All right, the last PowerPoint going through all of the traditional modules here as control systems and low voltage, other low voltage systems. This is not my forte. This is kind of its own industry in itself, generated generally from your mechanical systems because that was what originally required the most control. But now with how our technology is advancing and our capabilities, we have now started adding control systems to a lot of things. So pretty much anything that can be controlled will be. So I'll go through control systems a little bit right off the bat here, jump into the other PowerPoint once we're completed, but go into what control systems are, some of the essential components that complete your control system, the different types of control systems, and what BMS means, and all the different acronyms associated with that and the relationship to each other. So your control system is basically the brains of the operation. It bridges the gap between your environment and mechanical systems, environment meaning both exterior and interior. Okay, it's a series of devices that maintain, regulate, and improve efficiency and effectiveness of the building's MEP systems. Like I just mentioned, though, I've had projects where we've had point of sales added to control systems, we've had security added, we've had other things that were thrown into that control system because they are controllable, all in one package deal. So historically and primarily, we still only deal with MEPs when it comes to controls, but we can do a lot more. What we're trying to do is create that efficiency and effectiveness throughout the entire building's operation, though, is the primary function. So the main purpose of an automated control systems is to establish design conditions. So your design team will establish what those must be. Right? We ensure safe operation of equipment. We want to enhance energy efficiency. That's kind of what everyone's focused on with this in general. And then we want to also minimize human interference and or error with proper operation. One of the big things that, as you start building more large commercial operations or commercial facilities, we have thermostats and stuff on the wall, for instance. So that's part of your control system. And what a lot of people like to do is go mess with those thermostats, make things either hotter or colder in spaces. And in reality, there are set points behind them. And normally, even if you bump it up to like 75, it's probably only going to go up to about 71 or 72, just because if we allow everyone to have individual control over different spaces, the mechanical systems are not going to operate the way they need to. So even though it may say 75 on there, if that building's only designed to be operating at 72 max with the set point, that's probably only going to 72. So your essential components, we have input sensors. The next step is controllers. Then we have to have an output device. Then we have to have a communication protocol explaining what we're supposed to be doing with all that information. And then we have to have some way of us as the users connecting to all of this. So we have what's called a dashboard. The term I've always seen and used most is graphics. So the graphics are what we are using as the end user. So your sensors are the input device. They gather the information, whether it might be temperature, humidity, operation of equipment. We talked about daylight in other slideshows. Is it a CO2 monitor or occupancy monitor, something like that? Okay. A couple different types. We have a digital input, which is a two-state on and off, or we have an analog input, which is passive. Those analog ones do not require any kind of power supply or converter. So something that's more temperature sensitive, pressure sensitive, right? So the analog ones we also have an active version of your analog ones, which require power supply and converter. They look more like this. Your controller then, after the input device, right? So after we have a sensor that's collecting whatever information we have to have a controller, which is your actual brains of the system. That controller collects that data and decides how the system must respond with the data that's given. So what this is doing is providing signals for its output command. So your controllers look something like this. It collects data from the sensor and sends it out based on whatever our set points and design function is. So a couple different types for this. Again, we have binary, which is a simple two-position output, which is on or off function, or we have analog, which is varying or variable function. It's also been termed as modulating output instead of analog. So the next piece of that is the output device. So this is the output, this is the device along the line that carries out whatever the controller is telling it to do. So a prime example of what that might be is an actuator. So here's an example of what an actuator might look like, or a valve actuator. Um, so if the controller is saying, I need you to turn on, I need you to turn this temperature, the valve actuator is the device that actually carries out the command of that based on the sensor that the whatever the data that's being collected is providing to the controller. At this point, it's important to understand what normal position means. So normal position refers to however that device operates under normal conditions. So if the device is supposed to operate as normally open um, or normally closed, right? So it's important to note that it's an NO or an NC type function. So if you see something that's in normal operation and it's supposed to be open but it's actually closed, then we understand there's an issue with the system. The next piece is the communication protocol. So we have to have some sort of programming within the system that is the language that is spoken between all the components. That programming software and hardware is what actually talks to each other. So things like IP, IO, that's your internet protocol, your input output signaling, right? And then WAPs, so your wireless access points. Um, Sometimes interconnecting electrical and electronic to pneumatic or to digital control. So we're talking from across different types of systems. So a lot of our newest ones are digital. A lot of our older ones are pneumatic or electrical. So we don't always replace everything, but they have to be able to talk to each other. So we have to utilize sensors and have some sort of communication protocols set up within our programming software. This is where I have zero expertise in this. This is where we get a lot of software programming people to figure that kind of stuff out. Um, when it comes to programming, we have to understand the difference though between hardwiring versus wireless, right? So you might have a lot of WAPs within your facility, but if we have to hardwire it, we have a whole new type of coordination challenges we have to deal with. And the last piece is your dashboard or your graphics, whatever our user interface is. So this is your screens, your computers, whatever we are typing into. A lot of times nowadays, it's even just your phone that can do the simple functions, even some pretty advanced functions. So this is how we connect and talk to the system. Generally speaking, the more graphics we have equals more money. The higher quality we have of those graphics, more money. The more interface we have with those graphics, the more money. So if you want to save a lot of money on your control systems, you can reduce graphics pretty substantially. However, the less graphics you have, the less chance you have to actually run your system more efficiently. Not necessarily, it's just understanding how your system's running. So graphics are a good way to go. This is a pretty basic graphic example, just showing we have different equipment all throughout. So here's my chiller plant, right? That's talking to your different controllers throughout the system. And here's my site management portal. So, this is how we talk to the different system all throughout. It's not telling you a whole lot of information, but it's showing how it's all connected to each other through the entire control system. This one's a little more advanced. This one starts taking into consideration, outside temperature and daily activity, CO2 equivalents of the building, right? So sustainability indexes, showing how your financial reading, right, your return on investment might be, or how much we're spending on different, electrical or gas or whatever based on how the equipment's all functioning. So this one's just more like a general graphic overview of how a system might be operating in general. So building use status. Here's an example that shows, with the floor plan now getting a little more advanced where we have different VAV boxes all spread out and we can actually click on these in a real setting to see how, like, say, VAV3 in this zone is functioning. We can turn it on, turn it off, see how the function is actually working. We can see temperatures, humidity levels throughout. We can click on different floors. Obviously, this is just an image, but just showing how we can get a lot more detail, and then we can click through almost like you're just looking at a set of plans at that point. And now we can here's one showing how an actual boiler is working. So a water tube boiler, we can set up graphics to the point of every individual component within that boiler has its own sensors and controller and a controlling device that we can then communicate with to see how the whole system's functioning. So we can use these type of graphics like this to understand even maintenance purposes. When do we need to replace things? We can have things set up within our control system to show like exactly what's going on at any given time. Different types of control systems. We have, from the most basic to the most complex. We have self-contained, pneumatic, electromechanical, analog, electronic, and then digital. So more often than not, nowadays we're seeing what's called DDC, is direct digital control. That's our digital electronic type. We still have to deal with a lot of these, primarily like pneumatic and beyond, just because older facilities will still have a lot of these, and sometimes we don't replace them within, like renovations, so we have to tie into them and we have to communicate with them. So it's still a big deal. You still have to know how they all kind of work, just enough to understand the process. But DDC is typically what you see in new construction nowadays. Your self-contained one is basically combines a sensor, controller, and control device into one unit. Here's an example of one right here. So steam or a water system that uses temperature change to activate a control device is a prime example. So we have a little sensor here. We have the control device inside, the controller up at top here with a set point adjustment. So as that water system, if it's getting too hot or too cold, for instance, the sensor changes based on the temperature, and it kicks on what our adjustment and set point is to say I need a little bit more heat, or I need a little bit less heat within my system. Pneumatics are very common, especially in older buildings, but you'll still see quite a bit of them. They use compressed air to power and regulate the system. So the air is supplied to the controller at a constant pressure. The controller regulates the output pressure to the control device based on the changes in the load. So the standard type of mechanical controls that we use in the building, like I mentioned, it's still used in new construction, just very sporadically. Some of the people I use for my guest lectures that come in and talk about control systems still mention how they, you'll see them still on specs once in a while, even in brand new facilities, but not very common. So they're using this pneumatic valve here where we have a signal in the form of some sort of air pressure is applied to the diaphragm, which is up here in the housing, and that changes the valve's positioning. So they're actually quite accurate just because they're dealing with air pressure. Electromechanical control system use electricity as the power source instead of pressure. So the system typically has two positions, either on or off. The controller switches the control device. Like typically what we see is like a heating element in this case, right? So these would be on a lot of older homes, and most houses have historically used this type for their heating and cooling. Your analog electronic control is also quite common nowadays. So we use solid state components within that electronic circuit to create control signals in response. So if we have a sensor here, right, we put the set point on with these analog controllers, and then that is the device that controls then what's happening beyond. And our digital electronic, like I mentioned, is your most common. So this is our modern computers are programmed with sort of dedicated software and logic that we can control functions a lot more specifically by using that logic within the software. So just showing again how it all sort of comes together. Nothing new, nothing different. They'll do their goal is all the same. It's just the more advanced we get, the easier it is to control, the better options we have in play, and the better efficient, the more efficient we can operate our buildings with. Let's see, talked about some of this stuff. So some of the benefits, I kind of went through all this as well. So getting into BMS, and what BMS means, the Building Management System is sort of your unified approach to building energy use, climate control, and security. So we're kind of combining everything into one giant system. You will probably hear the terms BCS or BAS. Sometimes you'll see EMS or EMCS. A lot of times they're all interchangeable. They all technically mean something a little bit different. So a BAS system is technically the brains of the BMS system, but they are used pretty much interchangeably now because you can't really use a BMS without having that automation within it. So people just kind of use all of it. So that's basically combining everything into one general system. So what can it control? Pretty much everything, right? I've seen it, some of the more complicated buildings I've worked on, we can control use building use schedules, we can control maintenance scheduling, we can control energy consumption, security, all the lighting within it, right? Any mechanical or electrical component, point of sales, water flow, right? We're monitoring meters, our closed circuit television we can control. We can control elevators, fire alarm, the list goes on and on and on, right? But what we have to understand with control systems particularly is that as we start adding control, that means we're adding software, that means we're adding hardware, that means our costs up front is going up and up and up. However, what I've seen from buildings who and owners who have decided to put that money in up front, they have had plenty of long-term savings, and it's really pretty apparent pretty quickly too how efficient the buildings can run when you have really good detailed control over it. So example would this be VAV boxes. So going back to mechanical units, the more VAV boxes we have, the more zones that we have, the more cost it is. However, if we have a lot smaller areas to cover, the more control we can have over our facility, the lot more efficient that building will operate. So different items to consider when we're talking about controls, right? How high the quality of and the amount of graphics that we want. How many types of supervisory devices do we want? Are our items standalone or are we integrating them, right? Because standalone ones might cost a little bit more depending on how many systems we have to operate then. What type of project do we have, right? So some of them might not need that much control. Some of them might need a lot of control. It's not a one size fits all. Can you afford to spend upfront costs? And then how many zones are we talking about? So different things to consider. And that's all pretty much I have on controls. I know I kind of whipped through that one. Again, not my forte, my strong suit exactly, but definitely a cool system and something to understand how it works. I do want to get into your low voltage PowerPoint really quick as well. I don't have too much to go through on here. Just talking about different systems. The one thing I do want to get into a little bit is subcontractor coordination, just because historically low voltage systems are not always owned by the contractor. So a lot of times we deal with owners, subcontractors. So some of the primary types of LV systems, we talked about controls, but then we have communications and then life safety and security as well. So what is low voltage? So honestly, it depends on who you ask. So depending, and it also depends on the situation, because low voltage is relative term depending on how much voltage a system or a piece of equipment actually needs. So general designations for the National Electric Code indicate high voltage is anything that's from 1,000 over and over. Medium voltage is 50 to 100 volts, and low voltage is anything less than 50 volts, and this is talking about within a facility. So in general construction, we talk about LV needing anything that's about 50 volts or less. So same general concepts apply from electricity that we just talked about into low voltage. We're just utilizing a lot less power for applications. So a couple different types. We talked about control systems as well, so I'm not going to go through that. I do have a couple more. Okay, so communications. So this is when we start talking about division 27 within our specs. Controls are kind of spread throughout because if you need control over plumbing and mechanical and electrical components, you might have control specs within each of those. When you get to communications though, this is division 27 of your new specs. It can be made up of all these different things and then some, right? So data, voice, audio, visual, distribution and monitoring. So PA systems and address emergency communications. This is where things start to overlap a little bit. Healthcare communication, monitoring, clock systems all fall into communication. Safety and security is division 8 or 28 in your specs, right? And these are made up of things like access control, video surveillance, detection, alarming, monitoring. Again, some of the monitoring stuff can go between 27 and 28. And then life safety, emergency response stuff, fire, radiation, gas, everything like that. Some of the different materials, I can let you guys kind of read through this, but things like Cat5 and coax and HDMI and stuff like that will all be considered your LV materials. A couple examples of those as well. So you can see what we're talking about for different applications. An example here of which one might be high voltage versus medium versus low voltage, right? So as you see, just within a house, you have a whole bunch of different types of cables that might be needed for all those different applications. So I think this is a pretty good visual representation of how much infrastructure is actually hidden within any kind of facility. So again, like I mentioned, I want to talk about subcontractor coordination a little bit. Some of the most challenging things that you have to run into when it comes to low voltage is it's common to have different telecom, AV, fire alarm, security, and controls companies within any project. It's also very common to have the owner have direct contracting with a lot of these companies. The big reason why is because something like telecom, the owner might already have a communications company they work with all the time, so they're not going to bid that out. They might already have a fire alarm system that they already work with. So like for instance, at Northern Michigan here, we have one fire alarm system throughout the entire campus. So on any project that takes place on campus, we're just using that same fire alarm system. We're not going to start adding and changing things. Right? Same thing with security. Same thing with control. So like Johnson Controls does all of NMU's control systems. So they might have their own already, so they don't want you to bid them out. They're just going to want to use their own. The problems that come up with that then is we have a lot of different items that require a lot of some form of LV, some form of control, or some form of coordination. So, and then a lot of the systems have to communicate with each other. There's a lot of cabling that's required. And if the owner, for instance, has like say the AV contract under their own or telecom, well, we might have a bunch of areas closed in if they don't have all their ducks in a row and they have to come back and then we have to coordinate through who's doing what and when and where, and it's kind of messing with schedules. So that's where things get really challenging. I also like to bring up doors a lot in different projects or different classes because doors fall in line with a lot of things. It's a safety mechanism, it's a general trades type thing, it's MEPs because we have a lot of electrical stuff that takes place. Our mechanical systems affect doors with their ability to close and open properly. But with a door, I've had up to 13 or 14 subcontractors work on one door just based on how many different things we had to deal with. So with electronic strikes and monitoring and surveillance and access to card reader access, mag hold opens, all those different things, right? Fire protection, security. So they all come into doors. So the coordination there is very challenging. And then tying that back into, does my owner have that contract? Because if they do, I need to get some of this infrastructure in there early, and they might not even have their subcontractors ready to go yet. The other thing I want to mention too is the types of facilities that particularly require a lot of LV: data centers, hospitals, and schools. So you think about, safety, security, any kind of LV infrastructure. Data centers obviously are LV primarily. Hospitals have a ton of communication, safety, emergency response, all that kind of stuff, and the same thing with schools and communication amongst all those things. So a couple examples, right? The top here is a data center. If you've never seen one before, all of that is, low voltage cabling coming in and out, and this is what it would look like on the inside of each one of those data boxes. Here's a low voltage cable tray in a hospital corridor. So just popping up any kind of ceiling panel within a hospital, you'll see so much infrastructure from your MEPs up above. So, all right, with that, that's all I have for you for your low voltage and controls. That is the last PowerPoint for you guys to go through. If you have any questions, please let me know.